In this video, we'll talk about the general solution process for solving constant coefficient systems where the eigenvalue is repeated. So what do we get in this case? Well, all the work we've done so far has shown us a way to approach this problem. Let's assume that we have a system, x prime is a times x, where when we do the eigenvalue process for a, we get a repeated eigenvalue, where the determinant of a minus lambda I comes out to be lambda minus r quantity squared. We have r as a repeated eigenvalue. Well, so first we want to figure out the solution corresponding to that eigenvalue in general. So we can find the eigenvector by solving a minus ri v equals 0, because r is our eigenvalue. And then our solution from this, we get x1 of t as v e to the rt. But then we need one more solution. So our work before has shown us that we can get this using a t e to the rt term and an e to the rt term. But we need a generalized eigenvector first. So then we can find a generalized eigenvector by now solving a minus ri times w equals v, where this v is the same v we found in the first step. So same matrix, new variable, and now our right-hand side is v and not 0. And once we have that, we know that our second solution will look like v t e to the rt plus w e to the rt. Where we got this by plugging in a guess like this and seeing what v and w had to solve. And it turns out they had to solve exactly these two equations here. V is the eigenvector and w is the generalized eigenvector, where it equals v and not 0. So once we have all this, we know what our general solution is going to be. The general solution will be x of t is c1 v e to the rt plus c2 times the entire x2 term vt e to the rt plus w e to the rt. Once you find v and w, that's your solution. All right, so for an example of this, let's look at this here. I have a system, vector x prime is -2, 1, -1, -4 times x. You should probably guess it's repeated eigenvalues, but that's okay. Let's see what we get. So eigenvalues first, easily given by determinant of a minus lambda I, which is going to be -2 minus lambda, -4 minus lambda, plus 1, which is lambda squared, plus 4 plus 2 is plus 6 lambda, plus 9, which is lambda plus 3 squared. So our repeated eigenvalue is -3. Now I want to find v. This involves solving a minus ri, v equals 0. My r is -3, so I'm adding 3 to every component. So adding 3, I get 1, 1, -1, -1, v equals 0, which tells me that v1 plus v2 must be 0, or I can take my possible eigenvector here to be 1, -1. Any choice you make here is fine, as long as you make a choice that satisfies v1 plus v2 is 0, it'll work here. Then we want to find w. I'm going to take the exact same matrix from this part here. I'm taking the initial version of that matrix. If I did any row reduction, I can't apply that here. I'm taking the initial version of that matrix. So my 1, 1, -1, -1 that I had from here before row reduction, and then on the right-hand side, I tack on this vector v. I can now row reduce this. 1, 1, 1, 0, 0, 0, and you should always get a free variable here. So what does this mean? This means that w1 plus w2 must equal 1. And I can take whatever I want to make that happen. So I'm going to choose w1 to be 1 and w2 to be 0. You could pick 0, 1, you pick 1/2, 1/2. It doesn't matter, they'll all work here. So my w vector is now 1, 0. You cannot scale this vector, right? Eigenvectors you could scale, because any multiple is still an eigenvector. But for this generalized one, you cannot. It depends on exactly what v was. You cannot scale it, you cannot shift it. It has to be exactly what it was based on the value v that you chose. So then, now that I have v and w, I can write out my answer. What am I going to get? Well, x of t is going to be c1 times v e to the -3t plus c2 times the entire second term, which is going to be v times t e to the -3t plus w e to the -3t. And that there gives a general solution for this problem. That's the general process for if you have repeated eigenvalues, what you do, and an example showing how this works out. The one thing to keep in mind that I will emphasize again, when you carry down to find w, you have to use the exact v you found in the first part and the exact same initial a minus ri matrix to pull that down. You cannot scale that or use the reduced version before you get to that point. You have to use the initial part, reduce the whole thing all at once to get to what w has to be for this kind of problem. There's your answer, there's the process, and there's what you get for solving out these constant coefficient systems where you have repeated eigenvalues.